Okay. Hello, Sanjay.
Hello, ma'am.
What do we do? As usual, nobody is there.
Yes,
We'll wait for 5 minutes, to
sure,
3 minutes, and then I will start.
sure.
Sai Kalyan, how are you?
I'm fine, miss.
So only you and Sanjay are there. Now I think I will start my class because initially we will just revise what we have already learned in D block. Sai Kalyan, were you there when I was teaching D block earlier, or you were not there?
The last class I was not there in the class.
Okay. Okay, so we'll quickly go through the slides of D block. So this is the periodic table, and these elements which are from group 3 to 12 in uh, period 4, 5, and 6, they are known as D block elements. They are called D block elements. Why? Because the last electron goes into the D shell. Okay. So these are the general, so because the last, and since they lie as a transition between the metals and the non-metals, we also call them transition elements. Uh, and their general configuration is N minus 1, D 1 to 10, and NS 1 to 10. So you know that like if I take the 3D series, the electrons will first fill in 4s and then they fill in 3D. So that is why this is the electronic configuration of the most common of the last two shells. This is how you write. Then uh, what these are the this is to show the elements in the 3D series. 3D series lies in the fourth period. and we call it a 3D series. We call it 3D because the last electron goes into the 3D shell. And I had given this sentence to you to remember the order. You should know all the 10 elements of the 3D series, that is scandium, titanium, vanadium, chromium, and all that. And their atomic numbers you should know by heart. Then you know that from 3D, when I go to 5D, there's some elements you can learn properly, like zinc, cadmium, and mercury. Their atomic numbers are easy to find. If zinc is 30, then cadmium will be 30 plus 18, that is 48. And then from cadmium to mercury, you add 32 more, so you will get 80. So from 3D to 4D series, if you go downwards, then you add 18, and then 4D to 5D, you have to add 32. You will get the atomic number of the element. Also, there is a question which is often asked very frequently, which says why zinc, cadmium, and mercury are not considered as D block elements. Can you tell me, Sanjay, why zinc, cadmium, and mercury are not considered as D block elements?
I'm
Sanjay,
sorry,
can you
ma'am.
answer? Why are zinc, cadmium, and mercury not considered as D block elements? Can you tell me the reason?
Sorry, ma'am. I'm not sure.
Sai Kalyan, do you know why zinc, cadmium, and mercury are not called D block elements?
They have a D10 configuration.
They have a D10 configuration. So since they have 10 electrons in the D shell, Sanjay, did you understand? All
Yes,
these, when you have zinc is 30, so its electronic configuration is argon, 4s2, argon is 18, then 4s2, 20, and 3d10. So all these have the last shell, they will have fully filled last shell. The last shell is D, and the D shell there will have 10 electrons, all of them, cadmium and mercury. And since they have fully filled D shells, they don't show characteristic properties of D block, and so they are not considered as D block elements. There is also a question that, copper, the configuration of copper is 29. Okay. So copper configuration is also 4s1 and 3d10. So this also has 10, but this is considered as D block element. Why? Because in one of its oxidation state, it has 9. Like if I take Cu2 plus, then its configuration becomes 3D9. So if in one of the oxidation states there is a incomplete D shell, then it shows the properties of D block element. So that is why we do not consider them, and these are not considered as D block elements. However, copper can be considered as D block element. So these are a few things that you have to remember. Okay, then let me clear this for those who. Okay. Then the next thing is filling the orbitals. So this also, importantly, you should see the configuration of two elements. One is chromium. Chromium configuration is 3d5 and 3d5 and 4s1, because half-filled orbitals are very stable. So chromium is a special case, and similarly, copper is a special case. Why these two are special cases? Because here you have half-filled, and due to half-filled and fully filled orbitals being more stable, the electron from the S shell goes into the D shell. So instead of having 4s2 and 3d9, they have 3d10. Okay, then, so this is what I just told you. Zinc, cadmium, and mercury are not considered as D block elements. Then, the physical properties of transition elements, we need to see the trends. So they are all physical properties, they are all metals, they show metallic bonding, and the number of unpaired electrons in the outermost shell decide, they take part in atomic bonding. So as the number of unpaired electrons increase in the outermost shell, the metallic bonding increases, and melting point depends on the intermolecular force which exists between atoms. You know that. So based on that, we decide the metallic bonding, the melting point. So this is the graph which shows the melting point. So the melting point, if you see the number of electrons, unpaired electrons, they increase initially. So scandium has one unpaired, titanium has two, and vanadium has uh, three unpaired electrons. So chromium, when you come, it becomes almost stable, almost like vanadium. Why? Because uh, half-filled shells are very stable. So those five electrons, although the number is more, yet there is a slight stability there. So those five electrons are reluctant to take part in metallic bonding, and so the melting point doesn't rise as much. Then again, when you come to manganese, you see a dip in melting point, because in manganese you have all the five unpaired electrons, which metallic bonding. So the intermolecular force of attraction is less, and hence the melting point comes down. And then again, after that, the number of unpaired electrons after manganese, if you leave, then here there are four, here five, here six. And then when you come to zinc, there are no unpaired electrons, and so the melting point of zinc becomes less than that of copper. And that is the same for all the series. Magnesium, manganese, technetium, and rhenium, they all have melting points are comparatively less than the previous one, because of extra stability of half-filled shells. You can see here, I have written the 10 elements and the number of unpaired electrons. So here it is 2, 1, 2, 3, and then 5, 6, 7, 8, and 10. These are the number of electrons in the outermost shell, and this is the number of unpaired electrons. So as the number of unpaired electrons increase, the melting point also increase. As the number of unpaired electron decrease, the melting point also decreases. So after iron, you see a small decrease, and then slowly when you reach zinc, there are no unpaired electrons, so the melting point decreases further. The same thing is true for another physical property, which is known as standard enthalpy of atomization. Atomization is the energy which is required to break down the uh, element into isolated gaseous atoms. Okay, so that is also similar to melting point, and you can see the graph is also similar. That also depends on intermolecular force of attraction, which depends on metallic bonding. And as the metallic bonding becomes stronger with larger number of unpaired electrons, you can see the melting point rises, and then it decreases as the number of unpaired electrons decrease. Okay, then the next thing is about atomic radius, which is very important. Atomic radius depends on the intermolecular force of the force of attraction between the nucleus and the outermost electron. That is called Zeph. Zeph is here. I have written this one. Let me. Okay, so this one here, you can see this is effective nuclear charge. Effective nuclear charge is equal to Z minus S. Z is the number of electrons in the or the atomic number of protons in the nucleus, minus S, that is number of shielding electrons. Number of shielding electrons are those electrons which come between the nucleus and the outermost electron. They are the number of shielding electrons. So as the number of shielding electrons increase, the effective nuclear charge, Zeph is the effective nuclear charge that decrease, because the nuclear charge, it is attractive force, it attracts the outermost electron, and the shielding effect is the effect of the intervening electrons which try to increase the size. So if if the number of shielding electrons are more, then the atomic size slightly increases. So we can see the two factors. the electrostatic force of attraction between positive nucleus and the electrons, and the mutual repulsion of electrons present in the size determining outermost shell. So what are the trends that we see? This is the typical graph. So if I take in green, you see the 3D series. So the atomic size generally decreases from left to right. So if you see here from scandium, slowly the atomic size is decreasing. Why? Initially, the atomic size is decreasing because the number of protons are increasing in the nucleus. And then as you come from iron to nickel, the atomic size is almost the same because the shielding electrons increase and they neutralize the effect of the protons which are being added. And then as you go further, um, the shielding electrons increase more as you go to the right, and that is why the size starts increasing because because of the repulsion. In case of zinc, there are 10 electrons in the D shell which repel each other, and they tend to increase the size. Okay, so this is described here taking only the graph of D block. If you can see that in between there are same number and then it starts increasing. All the reasons are given here. You have got this. I'm sure you have got this recording. You can go through it and see that. Okay. So these are all these questions we will solve when we go do the give reasons at the end. So this is just to quickly go through. Um, uh, Another thing that you see in case of 5D and 4D series is sudden contraction in the size. That is because of what you call lanthanide contraction. After lanthanum, the remaining electrons 14 electrons go into the F shell, and the F shell has electrons in F shell have poor shielding, and so effective nuclear charge increases, and so the size decreases. So this drastic decrease in size is known as, after lanthanum, is known as lanthanide contraction. So all these things are there. Then based on atomic size, you have to learn ionization energy. So when you remove one electron from isolated gaseous atom, it is IE1. When you remove the second one from a positively charged, it is IE2 and then IE3. Now generally IE1 is IE2 and then IE3. And ionization energy increases from left to right as the size decreases, but this increase is irregular. Why it is irregular? Because of the factors. One is it is inversely proportional to size or directly proportional to effective nuclear charge. It is inversely proportional to the shielding effect of inner electrons. The shielding effect of inner electrons is maximum if the electron is in s orbital, then it is in p, and then d, and the shielding effect of electrons in the f orbital is the least. Then stability of electronic configuration, extra stability of electronic configuration of half-filled and full-filled orbitals also we have to keep in mind. Then based on ionization enthalpy, these are a few things which I just explained to you. Then variation, you can see in this graph, the variation in this is how I said that there is irregular increase in ionization energy, and initially it goes along with the size. As the size decreases, the ionization energy increases, and then there are special cases somewhere which can be individually explained. Then there are certain questions like ionization energy of copper. Atomic size of copper is less than that of zinc, and so the ionization energy of zinc should be more than that of copper. But ionization energy of this size of copper is less than that of zinc. So ionization energy of copper should be more than zinc, but ionization energy of zinc is more than copper. So that reason is because this is the configuration of copper and zinc. When I remove one electron, it becomes Cu plus, and for Cu plus, it is 3D10. So from unstable, it becomes more stable, and here from stable it is becoming unstable, and that is why the ionization energy, first ionization energy of copper is less than that of zinc. So most answers have to be given based on this sort of explanation. So all those questions are there, as and when we come across them, we will. So like ionization, first ionization energy of manganese is more than first ionization energy of chromium. So this also, I hope you remember, manganese, this is the configuration of manganese, and this is of chromium. So when I form Mn plus, it becomes 3d5 4s1. From a stable one, it is becoming unstable. And here, from an unstable one, it is becoming stable. So from unstable, it is becoming stable. That is why this value here is more of chromium compared to manganese. So all questions have to be answered like that. Then we talk about oxidation state. So they show multiple oxidation states depending on the number of unpaired electrons in the last shell. So like scandium can show, all of them show +2 oxidation state because of removing the electrons in the S shell. And then because of the unpaired electrons in the D shell, they will show many other oxidation states. Manganese is the element which shows in 3D series. Manganese shows maximum number of oxidation states. Then there is trends in the oxidation states, that is all as depending on the number of unpaired electrons. So first the number of oxidation states increase, and then as pairing increases, the number of oxidation states decreases. So there are many questions you can answer based on oxidation state. If, say, for example, why is manganese a good oxidizing agent? Mn7 plus. Why is it a good oxidizing agent? Because it has a very stable oxidation state, which is +5, or it has a very stable oxidation state, which is +2. So it can get reduced easily to +2 oxidation state from 7, and that is why um, uh, it is um, it is considered as a good oxidizing agent. Chromium is also a good oxidizing agent because it has +6 oxidation state in potassium dichromate, and it can change into +3 oxidation state, which is also a very stable oxidation state. So like that, you can describe oxidizing and reducing agents. So so there are many questions like this. We have discussed all of them. Now we will discuss some more. Then trends in electrode potential. This is also very important. So when we look at electrode potential, I explained to you, this is when we have to understand what delta H is, the energy which is given out when a metal atom in its solid state changes into, loses electrons and changes into hydrated ion, Mn plus, plus Ne minus. So this delta H is not just, I mean, it is equal to a sum of several energies. One is the enthalpy of sublimation, because it is in solid state, so you have to give energy to change it into um, isolated gaseous atom. Then, so that is energy of atomization. Then you have to give ionization energy to remove one outermost electron, and then hydration energy when it from gaseous state it changes into aqueous state. So this is what I have tried to show here. This is a metal which is solid. So you give atomization energy, it becomes metal in gaseous state. Then you give first ionization energy, it will become M plus. If it is changing into more stable M2 plus, then another ionization energy. And once it forms a gaseous metal ion, then it gives out uh, hydration energy to change into aqueous. Now this hydration energy is released, so that is negative, and these energies are given to the system. That is why they are positive. So the sum of all these energies that decide the value of delta H. And this value of delta H is important to understand the electrode potential. So if delta H, the negative value of delta H is high, then the negative value of the electrode potential. Electrode potential is generally taken as reduction potential. Then the reduction potential will be high. And if reduction potential is high, then its reducing nature of the metal will also be high. So if the negative value of reduction potential is high, then the reducing nature of the metal will also be high. So all the metals which have high negative values like sodium, lithium, potassium, they are strong, um, what you call, they are strong reducing agents. So now there are questions on general trends. So this shows the general trends in the what you call oxidation potential. So why it is different for as you go from left to right. All the trends are described here. So first is the as you go from left to right, the negative value of E0 it decreases. Okay, so um, Mn, the trend breaks. So when you come normally, when you go the negative value you can see is decreasing. 1 minus 1.63, then minus 1.68. The negative value is decreasing. So, but when you go from chromium to manganese, it becomes from minus 0.9, it again increases. So there is a break in the trend. So what is the reason for break in the trend? The delta H2 is less than expected because of stable D5 configuration. So anything relating to manganese is always about the D5 configuration. So here also Mn plus 2, Mn2 plus, the energy required is very less because from an unstable configuration, it jumps to a stable configuration. So since one of the values here, you can see the value here is changed. That is why the delta E value is more negative than the previous one. Then zinc, the trend breaks, the negative value increases again from 0.25, you see it is increasing down because of a stable configuration. Delta H2, that is the energy which is required to convert Zn plus to Zn2 plus is less than expected. Then nickel to cobalt to nickel, there is a very little increase. That is because hydration energy of Ni2 plus is more negative than expected. Then here you see all the reasons are given. Sanjay, are you there? Sai Kalyan has gone, so I don't know whether I should
I'm there, ma'am.
continue teaching. Yeah. And when you are about to leave, Sanjay, please let me know because I don't want to sit here with no student. So
Yes, ma'am.
I will, yeah. So these are all special trends. The very important question is where all of them are negative, but copper has a positive reduction potential. Why is that? Copper has a positive reduction potential because the hydration energy, see, second ionization energy is very high for copper. Why? Because from Cu2 plus it is changing to, so from 3D10 it is changing to 3D9, so you have to give a lot of energy. And so delta H is some of these minus hydration energy, and this is positive. So E will also become positive. So reducing nature of copper is very less. It is unable to liberate hydrogen from acids. Okay. Then reactivity of the metals also depends on the tendency of losing electrons, and reducing nature of the metal directly proportional to the negative value of E0. So based on the negative value of, as the negative value of E0 increases, the reactivity of the metal also increases, right? So if you look at the table of electrode potential, the elements which are on the top, which have the negative reduction potential, they are more reactive than the ones which are at the bottom, which have positive reduction potential. So you can arrange them in the order of their reactivity. Copper is the least reactive in 3D series. Why copper is the least reactive in 3D series? Because it has a positive reduction potential. So that is why when you react all the metals with acids, they displace hydrogen, but copper is below hydrogen, and that is why it cannot displace hydrogen. Then they all show magnetic properties. There are two magnetic properties, paramagnetic and diamagnetic. So paramagnetic is when um, paramagnetic is a property when all there is at least one unpaired electron, and diamagnetic is when all are paired. And you can, based on the number of unpaired electrons, you can write mu is equal to square root of n into n plus 2. And you can find the number of unpaired electrons by writing the electronic configuration, you will know, and then find the value of mu. So the trick here is that whatever the value of magnetic moment you get, the number before the decimal will be the number of unpaired electrons. So we can. So this is catalytic properties, and they all act as catalysts. They form complexes. They form complexes because they are small in size. They have unpaired electrons in the D shell, right? And high nuclear charge. Okay, they form colored ions. We have learned in transition in coordination compounds because of DD transition. And this is showing DD transition. So now we will do a little bit of a few questions. I think that will help you more. So stop share and I will share another screen. Okay, so these are the questions that we need to do. Give reasons of the following. Transition metals form complex compounds. Tell me, why do transition metals form complex compounds? So transition metals, they form complex compounds because um, because of three reasons. So first question, there are three reasons. First, due to vacant d orbitals. Vacant d orbitals, right? And the other reason is because they have a small size. And the third reason is due to high nuclear charge. Okay, they have high nuclear charge, so the size becomes small and they are able to attract ligands into their vacant d orbitals. So that is why they form. Now values, E0 values of Zn2 plus to Zn and Mn2 plus to Mn are more negative than expected. Okay, so Zn2 plus to Zn is 0.76 negative volts, and Mn2 plus to Mn is minus 1.18 volts. Okay, so they are more negative than expected. So this is because of uh, stable configuration, this Zn2 plus to Zn. This is because of Zn having 3D10 stable configuration. And Mn2 plus to Mn, it is Mn has 3D5, which is a very stable configuration. So when you have to remove electrons from a stable configuration, you require a lot of energy, and that is why you have to, the value of delta E becomes negative. Okay, value of delta E becomes negative because you are removing an electron from a stable configuration. Here again, you should remember that um, um, whenever there is any question relating to zinc and manganese, the answer is always half-filled shells and full-filled shells. Okay, so you should remember. If you don't remember anything, you should take a chance and write that. Then the third is actinoids show a wide range of oxidation states. So they show many oxidation states because they have unpaired electrons in actinoids can have unpaired electrons in 5f and in 6d and is in 7s orbitals. So there are three orbitals in which you can have unpaired electrons, and that is why you can have uh, um, large number of oxidation states, right? So that is why actinoids show wide range of oxidation states. Then here, explain the following observations. Just 1 minute, I'll increase the size. Okay. So the elements of D series exhibit a large number of oxidation state compared to the elements of F series. So in D series, there are large number of unpaired electrons which take part in bond formation due to less effective nuclear charge. Therefore, number of oxidation states are more in um, therefore number of oxidation states are more than F block where there is effective nuclear charge, right? So in F series, what happens? The effective nuclear charge is more. Why? I told you what is effective nuclear charge. Zef. Zef is equal to, this is, we are answering the first one. So Zef is equal to Z, which is the nuclear charge, minus S, which is the shielding effect. So the electrons S, if the S becomes less, then Zef increases. If Zef increases, then nuclear charge decreases. So if the electron is in the F shell, the shielding effect is less. So in F block, what happens? In F block, the electrons, F electrons have poor shielding effect, have poor shielding effect. Okay, so since the shielding effect is poor, that is why the effective nuclear charge is more. That means the nucleus pulls the outermost electrons closer to itself. And if the outermost electrons are close to the nucleus, then they will not form, they will not be removed easily, and there will be lesser oxidation state. But in D series, and if I compare D and F, in F, the effective nuclear charge is more. In D block, the D electrons do not, they have less shielding, but in F, it is more shielding. So Zef can be less than in case of F. So that is why they exhibit larger number of oxidation states. So if you have to write in one line, you should say effective nuclear charge in D series is less than the effective nuclear charge in F. That is why. Then copper salts are colorless, whereas Cu2 plus salts are colored. So you have to write the electronic configuration. So in Cu plus, what is the electronic configuration of Cu plus? It is argon and 3d10. That is Cu plus. And Cu2 plus, what is it? It is argon and 3d9. So if, sorry, 3d9. So if it is unpaired electron in the D shell, then only the electron can, from the lower orbital, if there is vacant D shell, vacancy in the D shell, then only there can be D-D transition. So D-D transition is possible in copper. But since this all the D shell electrons in the D shell are full, all the D shells are full of electrons, so there is no vacancy, so the electrons can't jump. So this is colorless and this is colored. Okay, so because of having a vacancy in the D shell. Okay, then the next one is assign reasons. Assign reasons. Mn2 plus compounds are more stable than Fe2 plus compounds towards oxidation in their plus 3 oxidation state. How will you explain that? So Mn2 plus, and this is Fe2 plus, right? So what is the configuration of Mn2 plus? It will be Mn2 plus is argon and sorry. So Mn2 plus is argon and 3d5, right? And Fe2 plus is what? It is argon. This is 25 and this is 26. So the Fe2 plus is argon and 3d6, right? Now to make it go to the +3 oxidation state, it has to lose one more electron. So Mn3 plus will become what? It will from d5, it will have to become 3d4. And Fe2 plus, what will it have to become? Fe3 plus, and that is 3d5. So from 3d6, it is going to 3d5. From here, 3d5, it is going to 3d4. So that is why, since Fe2 plus is going towards a more stable oxidation state, uh, their Fe3 plus is more stable, but Mn3 plus is not more stable. So Fe2 plus 3 plus is more stable than Fe3 2 plus, but Mn3 plus is not stable. You have to always explain with the writing the electronic configuration and showing the half-filled orbital. Then interstitial compounds are well known in transition elements. So this was one, this is two. So what is an interstitial compound? Interstitial compounds are those where, small elements fix in the crystal lattice. So all these elements, they form, they have almost similar size. So if this is, say, copper, right? So another copper, this is how you show what the crystal lattice. So in the vacancies, vacant spaces, some other metals, smaller metals like carbon can fit. So this is the interstitial compound, like steel is an interstitial compound. In the crystal lattice of iron, carbon atoms, they come and fix there. So because they have vacancies in which small elements can fix, that is why they can form uh, uh, very good interstitial compounds. In aqueous solution of potassium chromate is yellow, but it changes its color on decreasing the pH of the solution. So the third one, let me explain. So in aqueous solution, potassium chromate. So chromate ion structure is like this, Cr. This is O. It has a tetrahedral structure like this, right? And this is yellow. Now, when I change the pH, that means decrease the pH means I make the solution acidic. Then it changes into a dichromate ion. So dichromate ion is Cr, O here, here, and here. And another O here, Cr, O, O, and O. This is orange. So since CrO4 2 minus changes into Cr2O7 2 minus in acidic medium. That is why the color changes from yellow to orange by decreasing the pH. Now there is one very good question which is asked here, that of CrO4 and Cr2O7, which is a good oxidizing agent. Now Cr here, both have oxidation, in both of them, chromium is in +6 oxidation state. You can calculate and see. Here also chromium is in +6. Here also chromium is in +6 oxidation state, right? Now, why is it a good oxidizing agent? Because from +6 oxidation state, chromium easily changes to +3 oxidation state. Why is +3 oxidation state of chromium stable? It is stable because the the three electrons which remain. See, uh, chromium is 24. What is the configuration of chromium? It is argon, 4s1 and 3d5, right? If I write Cr +6, then what is the configuration? It will be argon. All the electrons of this shell are removed. So this is obviously very stable because the configuration becomes like argon. In +3 oxidation state, what do you have? Chromium +3 will be argon. And then 3, you remove 1 from here and 2 from here. What will remain? 3D3. Now the 3D3 is half filled T2G. Okay, when it splits, 3D shells are at the bottom. So half filled T2G. Okay, so half filled T2G, what does also is stable. So chromium in +6 oxidation state can easily change into chromium in +3 oxidation state, which is also stable. So when it goes from higher oxidation state to a lower oxidation state, that means it can be reduced easily. If it can be reduced easily, it is a good oxidizing agent. So chromium is a good oxidizing agent. But Cr2O7 is a better oxidizing agent than CrO4. It is because the bond Cr and O bond length here in the center, this bond length here, is longer than the others. And so this oxygen can be given out more easily. And so chromium Cr2O7 is a stronger oxidizing agent, or is a better oxidizing agent. Okay, now this is also a very, very important question which is asked very often, which I have taught you. You can see, I mean, there's nothing to repeat it again. That is preparation of potassium dichromate from chromite ore and potassium permanganate from pyrolusite ore. Okay, so chromite ore is FeCr2O4 and chromite ore is MnO2. So how do you prepare potassium dichromate from this and potassium permanganate? There are three reactions for each one. Write and learn all those reactions. That will help you. Every year one or the other is asked. Okay, so that is exactly like what is given in your text, or you have seen you can see in my PPT, you
Ma'am,
will know. Yes,
ma'am, that
tell me.
question you are asking board, ma'am. You're saying about the boards?
Yes, in the boards. In the board exam, there are two questions. One year they ask, how will you prepare potassium dichromate from chromite ore? Next year they give, how will you prepare potassium permanganate from pyrolusite? And this is always a 3-mark question. You can easily get it. It comes directly. You see the previous year's question papers, it is asked very frequently. So you will
Ma'am, they will
know
ask it directly.
directly. How will you prepare potassium dichromate from chromite ore is a direct question. Okay. So there are 3 steps. If for this one, there are 3 steps. So this is chromite ore is FeO plus Cr2O3, mixture of 2. So how do you start writing? I will just show you chromite, then potassium permanganate you can see later. So FeO gets oxidized first to give you Fe2O3, right? So this, so if I make it 2 here, and this, so this is 2 Fe2O3, so 4 FeO plus O2 will give 2 Fe2O3, 4 plus 2, 6, yes. And then Cr2O3. It is oxidized in presence of oxygen and Na2CO3, right? So you have to write a balanced equation. This will become Na2CrO4 plus CO2. Okay, so even if you don't write a balanced equation, you have shown how chromite ore will give you sodium chromate. Okay, so this sodium chromate in the second step, Na2CrO4, right? Na2CrO4 plus H2SO4. In acidic medium, chromate changes into dichromate. So you will get Na2 2Na2CrO4 will give you Na2SO4 plus Na2Cr2O7 plus H2O. Okay. And the third step here is easy, Na2Cr2O7 plus potassium chloride, right? It will change into K2Cr2O7 plus 2 NaCl, and then by fractional crystallization, you will get potassium dichromate, which is less soluble than sodium chloride. So sodium chloride will remain in solution and potassium dichromate will crystallize out. So these three reactions, they are important in preparing potassium dichromate. Similarly, from KMnO4, you have to prepare. From MnO2, you can prepare KMnO4. There are two reactions. First, in alkaline medium, you oxidize it, make it magnate ion, and then magnate ion in alkaline medium changes into permanganate ion. So these are two reactions you should learn. Then this one here, E0, this is E0. So E0 Mn2 plus M, that is reduction potential of copper is positive. What is the reason? So as I told you, this I have already described. So only copper has uh, a positive value for reduction potential in the 3D series. All others have negative value. What is the reason? The reason is that this E0, it depends on, you should write these points. It depends on delta H sublimation. Okay. So delta H depends on what? Delta H is the sum of delta AH, that is energy of atomization, plus delta H1, which is um, IE, delta H IE1 plus delta H IE2, ionization energy 1 plus ionization energy 2, minus delta H of this hydration. Okay, it is sum of all these three. Okay, so why do we take this as negative? Because hydration, it is sum of all, but hydration energy is negative, so we write. So sum of all these positive energies minus this one. Okay, now if this part is high and this part is low, then delta H will be positive, right? In most other cases, it is negative because hydration energy is higher. Now, in case of copper, this IE2 is very high. What is IE2? Changing Cu2 plus Cu2, Cu plus to Cu2 plus. You require a lot of energy. Why? Because you are removing an electron from 3D10 and making it 3D9. So the second ionization energy, which is required to convert Cu plus to Cu2 plus, is very high, and that is why the uh, mm, reduction potential uh, of copper is positive. So these steps you should, this is also a very, very common question, and which is asked many, many times in previous years' question papers. Okay, this Sanjay, I have already sent you board question papers, no, of previous years. Did I send you? Sanjay, are
Yes,
you
ma'am.
there? So from there, you can see this question has been repeated several times. Sai
Ma'am, even
Kalyan,
this
I
question is important, ma'am.
discuss the general characteristics of transition elements. See, this is a very general question. You know, this is atomic size, enthalpy of atomization, and tendency to form complex ions. So many together are not. One of them will be asked. Okay, so this is also, these are all previous year's questions. Some of them are previous year's questions. So atomic size, you can say, for take an example of 3D series,
Ma'am,
atomic size. Yes, tell me.
ma'am, is it as important as the indicate the steps of prep for KR2?
See, there are altogether 8 mark questions from D block,
Yes, ma'am.
right? So out of this, 3 marks are either potassium dichromate, A2Cr2O7 or KMNO4. Generally, they are asked every year, either this or this, 3 marks. 5 marks
Okay.
are for give reason.
Oh, okay.
5 marks are for give reason. That is what we are doing, give reason. In MCQs, they rarely ask D block. Okay, so 5 marks are for give reason.
Ma'am, so even this is equally important, ma'am. Is what you're
This
trying
is
to say?
equally, yes, equally important.
Okay.
Sai Kalyan, hello?
Yes,
Sai
miss.
Kalyan, if you can, if see for Sanjay, I have sent up to 2022, all the question papers, I have divided them into topic wise. So there is a document of several pages, handwritten document is there. If you want a copy of that, please send me your phone number in chat. I will note it down, or you can take down my phone number. Sai
I will,
Kalyan.
I will type my phone number in chat, miss.
Okay. So I will take it down. Please send your phone number. Where is the chat? So 9344458634. 9344458634. Okay. So I will send you all the notes and everything directly. Then it will be easier. This PPT
Ma'am,
and all I will send. Yes.
Thank you, miss.
ma'am, is even this question asked directly?
Yes, this question this question is, explain, only one of them can be asked. Either explain the trends in atomic size or a tendency to why they form complexes. This is common. Why they form complexes, I've already explained in the beginning. Atomic size also I explained. So atomic sizes is, they generally decrease, then there is irregular decrease. Initially it decreases, then it becomes almost same. Then zinc, when you go to zinc, the size actually increases. So all these things are very, very common things. They will definitely be asked somehow or the other. Tendency to form complexes, 3 reasons: small size, high nuclear charge, and vacant orbital. Same question is asked several times. Then this question is not a very common question, I think. I have not seen this question. Chemistry of actinoid is not so smooth like lanthanoids, because this is based on one sentence given in your textbook, which says that, which is written like this. So why is it so? Because actinoids are all artificial. Most actinoids, they are up to 92, that is up to thorium. They are up to 92, they are naturally existing. Otherwise, they are all radioactive elements, which the chemical properties of those elements are not studied, and they have unstable nuclei. All these elements which are actinoids after 92 to 118, they are unstable nucleus. And because they have unstable nucleus, that is why their properties are not well studied. Okay. Then name the members of lanthanide series which exhibit +4 oxidation state and which exhibit +2 oxidation state. Try to correlate their behavior with electronic configuration. Now here, the difference in this question and the way it is asked in the exam, they will give you names and atomic number of certain elements, and they will ask you which of the following will exhibit stable +4 oxidation state and which will exhibit +2. You are not expected to learn the names of all the lanthanides by heart. You need to know only you need to know only very few lanthanoids like that. Okay, so some important lanthanoids, I will show you their. Just 1 minute. I have written down So I will discuss students. Hmm. So this is should be after 60. Uh, so the lanthanides which exhibit +3 oxidation state is cerium. Cerium is 58, right? So here you should always learn to write configuration like this. Xenon is 54. So up to 54, you know. After 54, you have to start filling in 4 more. So how will you fill in 4 more? This will be, it is 4F, 4F, and then 5D, and then 6S. Okay, 6S fills in first, so 2 will come here. So 54 plus 2, 56. Then 1 will come here and 1 will come here. This is cerium, right? Now, since it has 4 electrons only, which can be almost same energy, so cerium 4 plus, what will be the configuration? It will be like xenon. So that is why cerium has a stable oxidation state. So remember this one, which is cerium. Okay. The other one is uh, promethium. Okay. So PR, promethium. Promethium is PR, and its atomic number is 59. So 59 also it has 5. So it is, how will it have +4 oxidation state? Just 1 minute. I'll have to see in the book. So this will be Xe, 4F, 5D, and 6S. So 6-X is full. D will be 0 and 5, 4F3. How can +4 be? Just 1 minute. I will show you the oxidation states of all of them. Stop share. Share screen D block. Not this one. This one. So zoom. Share screen. Let us go to the last part of it.
Miss,
Yes, tell me.
for promethium, the atomic number is 61, miss.
That's why I was thinking I'm making a promethium is 61. PR is what is PR? PR is PR is presodium. Okay, presodium. The question was which all have. So presodium has, PR has. Let us see why PR will have a stable oxidation state of 5, 4 plus 4. I don't know really. This is 3 and this is, so it can have maximum 5 oxidation state. Why +4 is stable, I don't. Terbium is, terbium has, so I am making a mistake. It is not this one, TB. Now, if you look at, can you see? Terbium can have a stable +4 oxidation state. Why? Because 2 will go from S and 2 will go from F. So 2, what will remain? 4F7. So 4F7 is a stable configuration. So the next one is terbium. So cerium and terbium, they will have +4 oxidation states. So they will be, their +4 oxidation states will be very stable. So these are the two questions that stop share, and then again share screen and go back to this one. So it is not promethium, it is, let me clear it. TB. Okay. So that is TB. So that is 65, and this is 4F9, and this one, and TB, TB4 plus will be xenon and 4F7. And so its +4 oxidation state will be stable. Okay, so try to correlate the type of behavior with electronic configurations. Electronic configuration here is like xenon, and here it is half filled. So these are these two elements, +4 oxidation state is very stable. Okay. Then what can be inferred from the magnetic values of the following complexes? So this I have explained to you earlier. You can see here. So what does magnetic moment of these compounds tell you? This magnetic moment is 2, here magnetic 2.2, 5.3 and 5.9. So this has 2 unpaired electrons, this has 5 unpaired electrons, this also has almost 5 unpaired electrons. So the number of unpaired electrons is what I told you when you know the magnetic moment, that is a value of mu. The number before the decimal tells you the number of unpaired electrons. So this tells you that uh, uh, this compound has 2, manganese has 2, and iron has 5 unpaired electrons, and manganese has also 5 unpaired electrons. Okay, this is what you understand. The next one is how the variability of oxidation state of transition element differ from that of p block elements. Can you tell me? I have discussed this. So in the variability in case of p block elements, you know what you see, if an element shows 2 oxidation states, then one oxidation state will differ from the other one by 2. Like for example, sulfur can show +2 oxidation state, it can show +4 oxidation state, and it can also show +6 oxidation state. Phosphorus can show +3 oxidation state and also +5 oxidation state. So these are p block elements. So in p block elements, what happens? Number of oxidation states differ from each other by 2. But in D block, the number of oxidation states differ from by 1. Like for example, manganese has +2, +3, +4, +5, +6, and +7 oxidation states. So they differ from each other by 1 number. That is the main difference. Then out of Cu plus and Cu2 plus, okay, which is unstable in aqueous solution, and why? So Cu2 plus is more stable in aqueous solution compared to Cu plus because of higher hydration energy. Higher hydration energy. So once this is formed, the hydration energy of Cu2 plus is higher than Cu plus. Cu plus. So in aqueous solution, Cu2 plus is more stable. Then orange color of Cr2O7 changes to yellow when treated with an alkali. It is same as I explained. Dichromate changes into dichromate. You can see it is, this question is also very important question. Then chemistry of actinoids is complicated as compared to lanthanoids because most actinoids are radioactive, so it is difficult to study their properties. Then again, explain giving reasons. Transition elements show many compounds in transition elements. They show paramagnetic behavior because they have many unpaired electrons. Okay, because the electrons in the D shell, there are 5 D shells, so the way they fill, you will get lot of unpaired electrons. Melting point of transition elements are high because of unpaired electrons. Their metallic bonding is very strong because unpaired electrons of the D shell also take part in metallic bonding. Then transition metals generally form colored compounds because of D-D transition. You can explain how there is a splitting, and because of the splitting there is D-D transition. Then again give reasons. The transition metals have high melting points. They again because of metallic bonding. So this question is also a very common question. Second and third transition elements have smaller radii because effective nuclear charge is more. Then second ionization energy is difficult from Cu and chromium, whereas it is easy for zinc. Because in Cu and chromium, you are going from D5 to D4, and in copper, you are going from D10 to D9. So that second ionization energy is high. And in case of zinc, the second ionization energy, you are changing from, um, um, you are changing to D10. That is why it is less. Most transition elements are paramagnetic. That is, I have just explained to you. And transition elements form alloys because all transition elements are almost of the same size. So when you are having a alloy, you are mixing two elements. So supposing you have an alloy of copper and zinc, the size of, so this is the lattice of copper. So supposing this is pure copper. Now it is not difficult to replace zinc. So you can just replace zinc because the size of zinc is almost same as the size of copper. There's not much difference in size. That is why. So since transition elements, they are of almost same size, they can form alloys effectively. Then this question, for M2 plus to M and M3 plus to M2 plus systems, E0 values of some metals are given, right? Use this data to comment upon the stability of Fe3 plus in acidic solution as compared to chromium or manganese 3 plus. Okay, so which is more stable, Fe3 plus or Cr3 plus or Mn3 plus in acidic solution? Okay, so now we have to explain that in acidic medium. I should write down all this. So E0 values of some metals are given. So Cr2 plus to Cr is given as minus 0.9 volts, and Cr3 plus to Cr is given as minus 0.4 volts. Which question is this? Stability of Fe3 plus in acid solution compared to Fe3 plus is definitely more stable. Fe3 plus to Fe2 plus is plus. Yeah, so this has a positive reduction potential. Since it is a positive reduction potential, its tendency to get reduced is is more. And so +3 oxidation state will be more stable. Wherever there is a positive reduction potential, the higher oxidation state will be more stable. Okay. And here, tell me, what were you saying?
Yes, I was saying Fe3 plus is more stable due to high enox.
Yes, same thing you were saying. So E0 value of Fe3 plus is higher. It is higher than Cr3 plus to Cr and lower than Mn3 plus to Mn2 plus. So reduction of Fe3 plus to Fe2 plus is easier than that of Mn3 plus to Mn2 plus, but not as easy as Cr3 plus to Cr2 plus. And that is why Fe3 plus is more stable. This is very obvious. Fe3 plus is more stable. They have given a lot of values, but that's not important. Now, can you tell me the answer of this one? In titration of...
I have a doubt in the last question.
Tell me.
Unless here they have given the stability of Fe3 plus in acid solution. How are we supposed to understand that it is a mineral acid or oxidizing acid? It can be also nitric acid or sulfuric acid. No, that means it is more negative.
Yes. So you have to assume that it is not an oxidizing acid.
Okay.
Because the next question is about that only. The titration of FeSO4 with KMnO4 in acidic medium. Why dilute H2SO4 is used instead of HCl? Now, this KMnO4 and FeSO4 in titration of that, why do we not use dilute HCl? We use H2SO4. Why don't we use HCl? Because HCl also gets oxidized and gives chlorine. Okay. So, in titration, what are you trying to find out? We are trying to find out the how much FeSO4 is oxidized by how much KMnO4. So if some KMnO4 will be used to oxidize chlorine, so HCl cannot be used as as an acid, right? So HCl also is an acid which can oxidize, which can be oxidized by KMnO4. HCl is also an acid which can be oxidized by KMnO4. That is why in titration we don't use HCl, we use H2SO. Right? Here you have to assume that it is not an oxidizing acid. It is sulfuric acid or dilute H2SO4. Most of the cases, when we talk of an acidic medium, we make the medium acidic by sulfuric acid. We don't make it by nitric acid nor by HCl. Okay, this for this reason, because most oxidizing agents, they will oxidize HCl, they will oxidize HCl also. So while you are trying to see how much of FeSO4 is oxidized, part KMnO4 will be oxidizing HCl also. So what I mean to say is, you are having a reaction between KMnO4, you want to find by titration, you want to find out how much KMnO4 is used to oxidize FeSO4. Now in acidic medium, there also we say only acidic medium. So we assume that H plus only is in the acidic medium. We don't consider HCl here. Here it is understood that it is dilute H2SO. Why don't we take HCl? Because KMnO4 can oxidize FeSO4. It oxidizes Fe2 plus to Fe3 plus, right? But it can oxidize HCl also. So it can oxidize Cl minus to Cl2. So you will not know how much KMnO4 has got oxidized by how much FeSO4 is got oxidized by KMnO4, because some KMnO4 will be used to oxidize HCl also. So you never use HCl. Okay. Why you don't use nitric acid? Because nitric acid will also oxidize FeSO4. Not only KMnO4 will oxidize, nitric acid will also oxidize. So we use only H2SO4. So if nothing is mentioned, you have to assume that it is sulfuric acid only. Then this is not printed correctly. Now there are some MCQs. Let us do. You want to do some MCQs? Kalyan, what is happening at your end? Your pre-finals are over.
You mean pre-board, miss?
Pre-boards.
That means one of them is over, another two to go.
Oh, you have 3 pre-boards.
Yes, miss, in our school.
Oh,
And in
wow.
middle we have practical examination.
Hmm?
In middle we have practical examination.
Yes, I wanted to ask you. That was my next question. You have practical exams. So literally you will be writing one exam every day of some subject or the other till your boards start on 15th, isn't it? Literally. Yeah.
Not literally, miss. In the middle we have lots of holidays. From February we'll be busy, but January month we are kind of free only.
So January month, do you have to go to school other than on days to write the exam?
Mm, no, miss. Other than exam, there's no working day.
Okay. So good, you are getting more time to practice. Okay. So let us do a few of these questions. Electronic configuration of a transition element X in +3 oxidation state is ArD5. What is its atomic number? Can you tell me? Hmm? In +3 oxidation state, it is Ar3D5. So what is its atomic number? This is easy for you, Sai Kalyan. So what will be it will be plus if it is Ar, it is Ar, hello? Niku, I'll call you in exactly 5 minutes. Okay? Okay. So this is Ar, it will be Ar 3d6 and 4s2, isn't it? So when I remove 3 electrons, it will become Ar3d5. So Ar is 18 plus 6. This is 6 plus 2. So it is 26. Answer is 26. Did you understand? Then electronic configuration of Cu2 plus is 3d9, whereas Cu1 is 3d10. Which of the following is correct? Cu2 plus is more stable.
Second option. Second option.
Cu2 plus is less stable.
No, no, no.
Then,
Cu2 plus is more
then
stable.
here also, stability of, see, the thing is, which is more stable? Cu plus should be more stable, isn't it? But that is not mentioned as one of the. Cu plus is stable, more stable. So Cu2 plus is less stable, right? See, Cu2 plus, what you are saying, Cu2 plus is more stable because Cu2 plus is more stable in aqueous solution. Cu2 plus is more stable in aqueous solution. But otherwise, Cu plus has a more stable oxidation state because of 3d10, right? So Cu2 plus is less stable. I think that should be the answer. I will just take 1 minute and check. This is 2. So NCERT. This is second question. Second one is 1. Second is 1. So just 1 minute. What did we do? Second is 1. Cu2 plus is more stable in aqueous solution. They haven't mentioned aqueous solution. So anyway, so Cu2 plus is more stable. That is the answer. Then metallic radii of some transition elements are given. Which of the following will have highest density? Density is mass by volume. So this is the element. This is the
Is it
atomic
iron?
radius. Tell
Is
me.
it iron?
Huh?
Iron miss, option 1.
Option 1, iron. It
Because
is
mass by volume.
126 mass by volume, no? So,
Volume only has radius in it. So inversely proportional.
uh, but mass here, which has higher mass, third. Question
Copper is iron mass.
4, 4. See, we have to find the highest density, it says, is of copper. Why did you say it is iron? Density is mass by volume, right? So here this is highest volume. How can it be copper? But the mass of copper may be much higher. I don't know. I'll have to look up this answer and tell you a good reason. Then generally transition elements form colored ions due to the presence of unpaired electrons. Which of the following will be colored in solid state? Difficult questions I found. CuF2. This has a fully filled orbital. This also has fully filled. This also has fully filled. It has to be 2. Cu2 plus. Okay, so it has 3D9. So it will have colored. On addition of small amount of caminophore to concentrated H2SO4, a green oily compound is obtained, which is highly explosive in nature. Identify the compound. I think it is Mn2O7. This is 5. Answer is Mn2O7. Then magnetic nature of elements depends on the presence of unpaired electrons. Identify the configuration of transition element which shows the highest magnetic moment. Highest magnetic moment means it should have largest number of unpaired electrons. So largest number of unpaired electrons will be in 3d5, right? When you go to 7, then it has 3 unpaired, 3d8 has 2 unpaired, and 3d2 has only 2 unpaired. So 5 unpaired here. Here, this will be 3 unpaired, this will be 2 unpaired, and this will be 2 unpaired. Okay, so answer is 5. Now the last one, which of the following oxidation state is common to all lanthanoids? +3 oxidation state. All right. So see
Yes,
you
ma'am.
tomorrow. That is, tomorrow we'll do the same thing of electrochemistry. And I will
Okay.
read out this number to you, 93444586634, right?
Yes, ma'am.
Okay, so
Yes.
that's fine. So I'll close now. See you. Bye.